Hey everybody, today's our last day of quarantine 5114. So before we depart, I want to thank everybody for all of their patience and flexibility. It's always my goal just to present the material, put it out there, have discussions about it, work through a bunch of problems. And I think in some way we were able to do that. I'm okay with being pretty flexible on the grades this semester, but I want to explain how I'm going to go about all this. No final exam, so we're going to not do that. However, I will provide you some questions. So on the day, I don't remember what it was, that I'm supposed to issue your final exam in the next few days, I'm going to send you questions. So you can kind of see what a final exam would look like. I'll probably send over 8 to 10 questions like I did midterm 2. You do not need to return these to me. So those are for you. If you'd like next semester to talk about these problems and go through all that and make up for that attention that we haven't been able to provide you on an individual basis, we can do all that. So I would say the best policy right now is keep studying, keep reading, keep working on problems. That's always true. And so chip away at this stuff. And always come back and reflect on it. It took me a long time to really sort out what our textbook was telling us. There's a whole bunch going on. I'm going to try to summarize that in just a moment, what we learned in this class. I will be a little bit more specific about grades. There's 4 things I'm going to look at when I do your grades. I'm going to do these in the next few days. Again, I don't need your final exam. I have everything I need to grade you right now. But if you haven't turned something in, you've got to do that real quickly if you want me to score it. If you want to improve something in the next couple days, I'll allow you to do that as well. And so if you think you haven't been as professional as you need to be on the EM project or the Delta Method project, you can update your drafts to me. Okay, so I'm going to be looking at your submitted problem sets through spring break. So just the hand-in problems that you were doing from Casella and Berger and the few that I appended to everything. So I didn't collect any after spring break. I do appreciate some of you sent some over, and that's good. But you didn't need to do that. So I'm going to be looking to see if you've turned everything in. EM project and Delta Method project, I'm going to be looking at those a little bit more carefully. So I want to see if you made real formal conclusions and we're able to really address in a simulation study how these two algorithms really work. This is the delta, Bayes, and Moot problem, so there's a little bit more here. So I'll say delta, Bayes, and bootstrap. So I was kind of hoping you guys would impress me with a little bit of effort on these. So I'm going to look there. I can kind of tell you that if you did a really good job on these two, I'm going to give you an A. And if you kind of just barely went through this project, I'm going to look a little bit more about your punctuality and things like that. Again, if there's something up here that you want to improve, you still have a few days. And then I'm going to look at your turned in midterm 2. And so I'm just going to see if you've got reasonable answers in there and you know what's going on. This was pretty open-ended, so I'm really just kind of looking for, did you put thought into your answers? Can I see that you gave me decent answers? If you wrote down for problems 1 through 10, X bar, X bar, X bar, X bar, it comes up a lot, but it's not the answer to every problem. I'm going to be a little bit more critical. So just some mild attempt at answering the question. You don't have to explain everything, you just have to put down your answers. Again, most of the weight is here, so on my homeworks. Okay, I think I want to get on with what we said in this class. What were the overarching principles? So I wrote down 3 things. So in the beginning of the class, we were kind of quantifying variability. Stochasticity, what is the distribution? So if you have an estimator, something that you're going to plug data into, that thing moves around. And we have to understand how it moves around, i.e. what is its distribution. And that's essential. Quantifying uncertainties, and that's what makes a statistician a statistician. So if you're doing that, you're a statistician. That's all there is to it. And there's a lot of ways you can do this. So you can do this mathematically. So sometimes we have asymptotic properties, or we can do things by direct transformation, or we have approximations. Central limit theorem, real big deal. So it's pretty amazing. Under pretty loose conditions, i.e. variances exist, averages are very well behaved and easy to describe what the variability is. It's normally distributed. But sometimes you can't do all the math. And so you have to move to algorithms like the bootstrap. And so we barely touched on the Metropolis Hastings algorithm. We said what it was very briefly. But there's a lot of algorithms you can do to squeeze out answers without doing all the calculus by hand. A lot of times we have to go into our algorithms if we're using them and show mathematically why they work. So there is a math problem here all the time, but once you understand what the properties of your algorithm are, then it's just as exercise in implementation. I'd like to say likelihoods are always useful for quantifying uncertainties. I understand that I might be a little bit skewed in the way I go about business, but I would say likelihoods are just always useful. So if you do things like MOM estimation or whatever, always check out the likelihood-based approach as well and compare those answers. So why I like likelihoods is they impose the right restrictions on the parameter space and the association with the data. So maximizing these things can be a good idea, but we've also studied methods where we penalize the likelihood. There's a lot of ways to do that. A Bayesian is pretty straightforward about it. Once they add their constraint, i.e. they multiply the likelihood by a prior, they describe that thing as a probability distribution, i.e. Bayes' theorem. But I would say the fundamental thing here is likelihood functions. They're the big drivers. So, sometimes likelihoods induce really good estimators just on their own. Saying that, sometimes you have to add a penalty to it to get a really good likelihood out of it. We study principles that say that maybe this is a good idea, and we've looked at a lot of examples, compared a lot of examples, and I think we've gleaned through this quite often that likelihoods are a good thing to work with. So if you want to move into your future, the question I always ask myself when I see data is, what is the generating process? And so I come up maybe with some hierarchical model. And then I see if that generates data that has similar characteristics to a data set that I'm studying. Do the parameters make good physical sense? Are they just statistical things that I'm imputing into models, or am I trying to characterize something physically? Once you do all of that, and you describe that process, that same functional form produces your likelihood function. So I'm always thinking about what is the distribution of the data, how do I model that? Where are my knobs, my parameters? Once we do all of that, we've effectively specified our likelihood function. So in practice, this doesn't happen just once. I usually write down simple models. I see if it looks like the data, and if it doesn't, then I enhance everything. So in practice, you don't get the distribution, you're going to build it. Once you do that, might as well use it for your inference. Decision making. We've talked a lot about that in different contexts, in either estimating parameters or hypothesis tests. In either case, all decisions are trade-offs. So I hope you understand that. So in the parameter space sort of example, if I want to do really well over in this part of theta space, and I decide to bias myself to do well over here, I'm going to give something up over here. So if you want to bring down your risk over in one part of the space, you're probably going to bring up the risk somewhere else. Sometimes you say, maybe I want to make the same risk across the whole entire space. I want my risk function to be constant. And we kind of understood that there's some good properties from that you can get. Whether or not you're a minimaximizer or you're a Bayesian, see here it's questioning my language right there. Whether or not you subscribe to minimax theory and that's what you like, or if you're a Bayesian, same thing. You know, all decision, how do we want to operate in different parts of the space? And I think that as we kind of look out into the world, right now we see a lot of people making decisions and they're focused on one thing. And they're blind to everything else around them. And this is why people argue all the time. And so I think it's important when you end up making a decision to say where in the space you might be giving something up. And so that's always true. You can't just have this uniformly best decision everywhere. So you can't beat every estimator everywhere. It'd be extremely unlikely. If you had an estimator where you're beaten everywhere, you shouldn't even be playing around with that estimator in the first place. I will say you have to define your losses as well. So these trade-offs you have to quantify. And so if you don't do that, you haven't been explicit and you shouldn't be making decisions. And so you have to quantify how your decisions impact different parts of the parameter space. I think that's what we hear a lot when we watch the news, is people arguing about these trade-offs. It's impossible not to have the trade-off. Effectively, we proved that mathematically, that if you're going to try to do really well in the parameter space somewhere, you're going to lose somewhere else. So make sure you've picked that part of the parameter space for a good reason. Usually this is subjective. That's the way I see it. But sometimes you might say, well, I like things like L2 loss. It's easy to work with. Kind of gets me in the ballpark of a reasonable answer. I don't need to refine that anymore. I don't have any subjective knowledge about any of this. I would still say that's a subjective choice that you've made. So be prepared to defend it. If I'm using L2 loss, I probably have several reasons why I might say I've picked that. If I'm concerned that maybe there's some other reasonable loss function out there, I usually plug that one in too and see how it impacts my answers. And so I love doing this. Do a couple reasonable things, and if your answers totally change, you've got some more thinking to do. If your answers are all about the same, that's great. So I really like when that happens. Okay, down here I'm thinking more about the hypothesis testing sort of thing. So, are comparisons necessary? Do you have to always compare against something? And the way I stand on this is yes. So, if you just think about common English, when somebody says something is big or it's huge, it is compared to what? What are we talking about? If somebody says something is tiny, compared to what? And sometimes when we speak and we're a little bit informal, there's context in the situation. And everybody knows maybe what you're comparing to. And so there's a context to all of this. But in all mathematical problems, there's context as well. And you need to define what that is. So in hypothesis testing, we kind of looked at two different paradigms. The Neyman-Pearsonian is calibrating error rates. They're coming up with this cool tool for doing it. Keep in mind, likelihood functions appear in all of that. We talked about monotonicity of likelihood ratio tests. There's some problems in the book. But in the Sharp test, I at least argued a little bit against Neyman and Pearson. Keep in mind, Neyman and Pearson didn't say just compute a p-value and see if it ducks alpha. So when you do that, and that's all you do, you're not thinking about a comparison to the rest of the parameter space. And so Neyman and Pearson really described you should get the whole power function, and you should compute it over the alternative space. And so they advocate that you always look at the power everywhere. And so you're seeing this distribution of error rates depending on what theta was. Now, I personally don't look at that stuff, but I can definitely understand in experimental design why you might. You might say, I need to go out there, I need to get so many samples so I can guard against making certain types of errors. And in a well-designed experiment, I think that this is a good paradigm. If something that you can repeat over and over and over again. Keep in mind the p-values themselves depend only on h0. So, p-value. I wish we had more time to study some of this stuff, but with everything that's going on, we lost a little bit of time. But a p-value is the probability of your data and more extreme data given h that the null hypothesis is true. Usually what we're doing in the book is we maximize that probability over the range in the null space. So we look at the maximum error that you make right here. So the book goes through that and they put a supremum right in front of here over h0. My point is this, that probability only depends on h0 itself. The alternative isn't really used. It helps to guide us in the direction of more extremity, but it's not explicitly being used in the calculation. The power function does deal with it though. And so what Neyman and Pearson ended up saying, along with Wald, is they said, you don't want to just specify the alpha level and compute the p-value. You also have to look at the effect size. So how far away you are. And so what is that little gap? So in the example we were looking at, if x bar is very, very close to the null hypothesis, you need to say something about that. So that's the difference between the null and your sufficient statistic. And so without really saying anything about that gap and how big it needs to be practically significant, you're not making a comparison. Now I get it. I sympathize a little bit with Fisher here, where if this number is very small, the idea is the probability of your data and more extreme data, i.e. your data lives in a very small happens in a part of the space where things are very unlikely to occur, then there's probably something wrong with your specification. It could be your whole probability model, but the idea is that it's probably h0, and so you reject that. So that makes me think, when I end up saying something's not very good or I don't like it, am I actually doing a comparison to everything? Or am I just saying, look, this just doesn't look right, it's wrong. It's something different. And that's kind of what a p-value does for you, this Neyman-Pearsonian thing. If you just see if your p-value ducks alpha and you reject, you're just saying, look, it just doesn't look good. I don't want to compare it to anything else. I just know it's not this. And I've grappled with that statement in my head for a very long time. Is that something that people can actually do? I had the great privilege of having a conversation with Jack Good about this. And he kind of set me straight, and he's like, you can't do it. It's not possible. So when people are saying, this just doesn't look good, they've established some comparison. And I think he's right. I think you do have to compare. And so looking at the full power function is one way to do that and compare those different probabilities of rejecting for being in different parts of the space. Saw a very interesting talk by Jim Berger a couple years ago here on campus. This might have been last spring. And I was totally enamored by something he said. And he said, if you're going to use a p-value, compute a p-value under the null, compute a p-value under the alternative, and take a ratio of those two things, and work through those as a ratio. So I was really enamored by this because I wrote that down a long time ago. It's like the p-value ratio. It turns out p-value ratios, at least in these normal cases, are asymptotically equivalent to likelihood ratios. And so if you want to see a proof of that, I've got it written down somewhere. You can kind of think of it, if you think of that normal distribution curve, the height of the curve under the null hypothesis, that's your likelihood evaluation. The area to the right of it is your p-value. And so that height and the area have something to do with each other, as you can imagine. And asymptotically, they start looking very similar to each other. Bayes forces you to make the comparison. So where does the comparison happen? It happens in the alternative specification. And so that's what I'm always watching. When somebody's doing some sort of hypothesis test, I'm always watching how they built their alternative. How did they calibrate it? And so I believe we should be doing something similar to this, at least some comparison. It could be in likelihoods. So basically, in the simple versus simple test for the name and Pearson, you end up evaluating your likelihood under 2 points, and you take the ratio of that thing. That seems to be a reasonable thing to do. So we did argue that that doesn't have the same properties when you move to the sharp test, i.e. you test 1 point against an entire continuum. So there's more issues to think about there. Bayes has to deal with that problem as well. And they have a different mechanism to do it. And so really the Bayesian is telling you how much you believe something compared to everything you compared it to. And this stuff right here, if you just look at the p-value, it's only telling you something about the null space. We're not thinking about the alternative space. So there's no explicit comparison there. So just kind of going back through all of this, quantifying variability, decisions are trade-offs. That's always true, whether or not when you build estimators or you do hypothesis tests. And I want you to think about this. Throughout your entire career, do you need to make an explicit comparison? There are people out there that say you don't need to. I've at least stated my argument. So I think with that in mind, everything else is just practice. Practicing implementations, practicing problems. So any problem you see that looks a little bit complicated, but the answers look neat, try to work it out. So if you do this throughout your career, you're going to get good at it. In every Monte Carlo algorithm you've ever come across, implement it. If you do that for several years, you're going to get really good at this stuff. So you're going to be able to do both the math and the algorithms. You'll never get stuck on a problem. Keep in mind, this stuff down here, these are subjective things. You have to have scientific rationale for why you choose certain things. It's not just math. So usually I say statistics is at least 2/3 qualitative. It's all about this stuff, the trade-offs and losses, and that's what I think a lot about. It was need a scientist or an engineer to help me think about it. This is the easy stuff, but it's the stuff that gets us jobs. So work on that, practice, and hopefully I'll see you all in the fall. So if you have any questions, concerns, comments, send me an email. I'll be around all summer. Thanks, you guys.